All right, I'm going to do a little narration here. We'll record this in case we have a snow day on the last lecture of class. And if we are watching this remotely, I hope you are warm and safe. What we're going to do tonight is look at an example of how we would parallelize a problem that is not just a simple for loop, but actually a little more complex than that. And the problem that we're going to look at is the traveling salesperson problem. We'll explain what that is and then kind of walk through it. Before we do that, just a reminder, the homework is due this Friday at 5 p.m. That's Friday the 21st. I will be grading it very quickly. And so make sure that you turn it in on time. Do not wait until the last second. Once I start grading it, I will not accept additional submissions. And this is worth 20 points. So please make sure that you pay attention to that. And by hopefully Saturday at noon, you will know exactly where you stand going into exam two. If you have enough points and you already have an A, you don't have to take exam two. If you're not in that situation, you should have a pretty good idea what you need to get an A or what you need to move up to the next grade level. All right. What is the TSP, the traveling salesman problem, or the traveling salesperson problem, as they say in modern day? It's a problem that is actually so simple you can explain it to a 5-year-old. You have a bunch of locations, and someone has to visit every location. They're going to start and end at the same place. They cannot visit any place twice. So over here, you can see the map of Santa Claus. Santa Claus has a traveling salesperson problem. He has to visit all these places on Earth every night, every Christmas, and he has to get there. Many years ago, way back in the 1950s, there was a famous TV show called Car 54, Where Are You? And it starred two bumbling cops. And as a promotion, Procter and Gamble put out this prize that said, if you can visit all the cities on this map and start in Chicago and end up in Chicago, then you will win some, big prizes, probably some soap and other things. And so this is a very common problem. It turns out it's an interesting problem because it's not a problem that computers can easily solve. There's not really a good algorithm that can consistently beat just a brute force algorithm. And so as a result, it'd be a great one if we could parallelize it and make it go faster. Turns out that even the Mona Lisa has been put into the traveling salesperson problem. And here, what you can actually see is you can actually see the route. And what they did was they reduced the Mona Lisa painting to a bunch of pixels. And the computer that drew this, had to visit every pixel once and only once, and then return back to the same pixel at the end. And what you see here is supposedly one of the more efficient paths to draw the Mona Lisa. So very interesting problem, something everybody generally understands. Now, how will we solve it? The rules are start at any city, and that becomes your origin. Visit every city one and only one time. Return to your origin when you're finished, and find a route through all the cities that is the shortest possible route. It's a very common problem, not easy to solve. Order n factorial, which is just absolutely terrible. And no known algorithms, as I mentioned, can beat the brute force method. Interestingly, bees, when they leave their hive and go and visit flowers, they solve this problem instinctively. Their little brains, their little bee brains, are actually better at solving the traveling salesperson problem than computers. And so, what we really should do is just copy their algorithm and see what they're doing. All right, so here's our example. This is straight out of the text. Sorry about the black blob down there in the corner. That's supposed to be a camera, but my camera's not working. So I won't be able to draw for you with my camera. I'll try to draw some on the screen here in just a little bit. So there are 4 cities in the text problem, city 0, 1, 2, and 3, and the distance one way from every city to the next is shown. So for instance, this arc up here from 0 to 1 says the distance from 0 to 1 is 1, but if you're traveling from 1 to 0, it's a directed arc, and it tells you that that would be 5. So what is the shortest problem? Just pause the video just a second and say to yourself, I'm going to solve this, and see if you can come up with what the shortest. Maybe you will do visit 0, 2, 1, 3, and back to 0. And if you did, you would say from 0 to 2, it cost me 3. from 2 to 1 cost me 2. Now my total is 5. Now I have to go down to 3, and that cost me 6, which makes my total 11. And now I go back to 0, and my total was 18. Is that the fastest route? The answer, I think, is no, it's not. However, it would be a route that we would start with. And then you could say, okay, well, let me try some other ones. Let me try 0, 3, 1, 2. So that would be 8 plus 6 is 14 plus 2. That's going to be 19. That's not any better. So we can try and find a route. Now we can just sit here and play with it with our pencil, but there is a way to solve it using a directed or a tree. And what you do is you start with node 0, and we go to node 1. That's what this is showing us down here. Let me see if I can grab a pen, a red pen. This is showing us that I went along this arc from 0 to 1, and the value was 1, which you can see right there. And now from 1, I have two choices. I cannot go back to 0 yet because I haven't visited all the nodes. So I could go 0, 1, 2, and the cost there would be 0, 1 is 1, and I'm sorry, the 1 is off the map here. 0, 1 is 1, and 1, 2 is 2. So that total is 3, and the only option left now is to go to 3 and back, and that total would be 20. However, if I went 0, 1, 3, when I arrived at 3, I'd be at 7, and to go to 2, the total here would once again be 20. We can keep basically filling out this chart, and eventually we will find the shortest path. We can see a path down here that's pretty short, and that is path 0, 3, 1, 2, and that might be the shortest path. So basically, one of the ways we could solve this would be as if we created a graph, a tree graph, and each arc represented another hop, and at each hop we would have all the possible next hops, which actually would get smaller as we went along, because as we used each arc, like from 0 to 1, we would not be able to repeat any of the nodes we had before. So if one thing we can do when we're doing this is if we ever see, for instance, when we first go down this way, we see that the cost is 20. Well, now we go 0 to 1, and we see the cost is already 21, and we just quit. We say, hey, I'm not going to go any further. This is a dead part of the tree. So there's some things we can do if we're going to write a computer algorithm that will make it faster. And one of those things is we're going to keep track of the shortest path. And anytime we get longer than the shortest path, why, of course, at that point, we will quit searching that particular tree path. All right, so in this algorithm, what we're doing is we're doing a depth first search with elimination. And I've kind of shown that to you. I don't have a board to show it to you, but I've kind of tried to show that to you here on the slide. All right, now here is a recursive algorithm that does exactly that. Here is our function call up here. And we're going to have a special kind of a data structure called a tour T, and we're going to name it, the variable is going to be tour. All right. And we pass it a city. And now what we do is we start by saying, hey, our tour is going to keep track of the places we've visited. So when we first start, we're going to start at node 0, and our tour will have a 0 in it. And that's all it has in it. All right. It will probably have the cost in there as well, but the only node in it is 0. So the first thing we check, hey, did we get past a tour that has four nodes visited? If we did, we can check to see if that's a new best tour. And in this case, we have only one node. So we say, okay, well then for every neighboring city, if it's possible that this tour that we're looking at and visiting that city next would be a good tour, then we will add that city to the tour, call the depth first search, call ourselves, and then search all the possible. So what's going to happen? We're going to get down here. Our tour is, hey, sitting at 0. And it turns out that we're going to go for every neighboring city. We'll start at 1. So the first thing we're going to search is 1. And we say, hey, is it possible that we could search 0, 1 at this point? We say yes. And so we call back up here. And we now we come in with node 0, 1. Let me erase some stuff here. See if I can get that thing going. I'm going to get my eraser because I'm going to start over again here. Now I'm in the part of the stack where I'm going to get 0, 1. Now I come in, does 0, 1 have 4 cities? Nope. So now I come in here, would it be possible for every neighboring city, first neighboring city from 0, 1 is 0? Nope, that's not possible. We can't visit 0 again. So then we ask, could I visit 2? Could I go 0, 1, 2? And the answer is yes. So we're going to call ourselves with 0, 1, 2, which comes back up here again recursively, calls with 0, 1, 2. It says, does 0, 1, 2 have 4 nodes? The answer is no. So we come down here and we say, with 0, 1, 2, could I visit node 0? Nope, I can't visit 0 because it's already in the path. From this 2 on the end, could I visit node 1? No, can't do that. Could I visit 3? Yeah, I could visit 3. Now I come back up here again, and now I come in with 0, 1, 2, 3, and I say, hey, does this have 4 cities? Yes, it does. And now I say, is this my best tour? The cost for 0, 1, 2, 3 would be known to us. And we would say, yeah, this is my first time to have an actual tour, so it's my best tour. And now I would, because this was an else, I'd come back and I'd return to the depth first search and I'd say, okay, remove the last city. Remove the 3 from here. I'm going to do an eraser. Remove the 3. And this will this will then come back up here and say, oh, I'm done. So that would then return, and this would be 2. And now this guy would say, oh, I'm running my algorithm. I can put a 3 here. And he would recursively call himself with the 3, which would check. And so basically, this just keeps going back. If you have any questions about how this works, I encourage you to get out a piece of paper and just kind of follow the steps. Note that you're calling yourself here and you're passing the tour with the cities you visited. And whenever you get to come in here with 4 cities, you're going to run this part. Whenever you come in with less than 4, you're going to run this part and call yourself recursively. All right, so hopefully that helps. This is an algorithm that we can use. Over here on the right, I've explained a few things like feasible checks to see if it's adding the city that we're checking is valid. Okay. All right, so let's go to the next slide. So what we would do is we would just work this algorithm until we find a best tour. And this algorithm is not a terrible algorithm. It's brute force, but it is going to find us the best tour. Now, there are problems with this, particularly if we're going to try to parallelize this guy. The first problem is that recursion is extremely expensive in terms of resources. Calling ourselves requires stack space and time to change the context that we're in the middle of. So we have to, load a new program counter, and we have to copy all of our data structures to the new program space. It's quite inefficient. At any one time, and the other problem, this is the biggest problem for parallelizing, at any one time, the current tree is the only thing that's accessible. So this is like a single threaded line of code. Even when we call ourselves, it's single threaded. So unfortunately, it's not a very good algorithm for us to try to parallelize. And the main problem is the fact that we don't have, like, we have one data structure that's running in here, and it's going to be a real problem. Okay, let's see if I can pause this. I got a text. All right, well, that text I just got, it is actually currently 3:50 in the afternoon on Monday, and I was recording this on the chance that they would cancel classes on Tuesday, and indeed they have. So this lecture is going to be posted, and gosh, I really wish I could get rid of that thing there, but unfortunately it's not letting me do it. All right, so I'm going to pause this real quick. And we're back. So what I was explaining was that this particular algorithm does not really work well if you're going to try to parallelize. So let's see, what other options do we have? Well, we have an option where we would employ a non-recursive algorithm, where instead of letting the computer operate our call stack, we'll keep a stack ourselves. Now, in this situation, this really requires you to sort of work through it. In this situation, we are going to have a stack that keeps track of what city we're on. And the stack is going to help us keep track of where we're at and whether we've got a new best algorithm. Okay, so here's I'm going to get a pen up here. We're going to go through this a little bit at a time. To start the algorithm, notice this is not a function call anymore. This is just a statement right up here at the beginning. It pushes all three cities, uh, 3, 2, and 1 onto the stack. And so we have a stack, and the stack has, oops, on the bottom, we put 3, and then we put 2, and then we put 1. That's this step right here. We create the stack with starting cities. Now, as long as the stack is not empty, we're going to run this algorithm between steps 3 and 20. And so what happens? The first thing we do is we grab our current city. Our current city is now going to be, oops, it's now going to be 1. Sorry about that, because that's on the top of the stack. So we pop the stack. Popping the stack means erasing it. So we erase that, and we have our number 1 over here. And now let me get my pen back. And now if the city equals no city, no city is a special flag. I'm going to say it's -1, and we're gonna put that on there whenever we load a new level in our um, depth first tree. So if the city equals no city, we're going to remove the city we're working on, basically pop the stack and go down to the next one. In this case, the city we just popped is 1, so we're not going to do step 6. What we're going to do instead is we're going to add the current tour. We're going to add a city to our current tour, and that's going to make our current tour uh, 1. And we're going to put 1 on our current tour. That's the only thing that's on there right now. Does the city count that we have equal n? N is 4, by the way. There's a 4. Yeah, that's not bad. No, it doesn't. So we're going to push onto the stack no city. So first we put here no city. Okay. And then we say for numbers equal 1, n minus 1, which is 4 minus 1, that's 3, number greater than 1, we're going to subtract that. If it's feasible to add that city on here, we're going to do that. So, sorry, my puppy is wanting some attention here. Okay, I'm going to push the stack no city. I've got no city up here. Now I've got to say, is it feasible for me to push uh, city 3 on here? I could, because it's feasible to add a 3 to that 1. So I put a 3 here, and then I asked, could I push a 2 on there? Yes, it's possible for me to push a 2 on there. Could I push a 1 on there? No, I'm already at 1. Could I push a 0 on there? We have assumed we started at 0, so I can't push a 0 on there. So now what I'm going to do is, okay, I push that on. Now I return back up here, and I say, hey, while the city stack is not empty, you can see it's not empty, pop that next city. So I come up and I take the 2 off. We get an eraser, and I take the 2 off, and I put it onto my list of cities that I'm working right now. And it goes right here. I'm now working 1, 2, and I say, hey, was that a no city? It was 2, so it wasn't a no city. And then I'm going to add that. Now I'm going to be working 1, 2. Does the city count of this tour I'm working equal 4? Nope. So now I'm going to try to push stuff on again. Once again, I put another no city on here, and I've got 1, 2, and I ask, can I add 3? Yes, I can. I put 3 up here. And can I add 2 or 1? Nope, I can't. I come back up here. I pop the 3. There's the eraser. I pop the 3, and I put it onto my city tour. And by the way, this has a 0 built into it. So then I come back up here, and now I say, I pop that 3. Ah, good. Now I've got all of my cities visited from 0. And I ask, can I let's see here. Can I get the total? And I can. It turns out that the city count equals what I want. So I once again say, is this a new best tour? In this case, yes, it is. I have got a new best tour. And then it says, okay, well, remove the last, because this stores my 1, 2, 3, 0. Cool. And now he takes the 3 off. That's this step right here, step line 12. And then goes down to the bottom. And what is going to happen? He is going to pop back up here and say, hey, pop the stack. But now we have a no city. So we pop the no city, eraser, get rid of the no city. And since we got a new city, we're going to remove the last city. So that's how we get that three off of there. We remove the two, and then we go back through the algorithm again, and now we're going to add the three. And so that means we've explored the 1, 2, and now we're about to explore the 1, 3. I'm going to erase the 3 from here, and he's going to go down here and say, can I add a 2? And he's going to be able to do that. What he's going to do when he gets down here to the bottom, this area under lines 14 through 18, he's actually going to put a no city here and then city 2 and recursively go through this. So what this algorithm does is without using recursive calls, it instead builds a stack of cities, and the cities are added and then pulled off. And every time we add a new level, a level that would be a level in our search tree, we put a no city on there. Again, I encourage you to take a little bit of time and open the text. This algorithm is described. Look on the slide and say, okay, what are these lines doing? And just sort of work it for about 2 or 3 minutes. You'll get a very good feel for what's happening here and understand this algorithm. And we could work this algorithm until we found a best tour, and it would just take us a little while. This algorithm is reasonably efficient. All right. Now we're going to look at a third algorithm. This is a different approach. And in this one, it's kind of similar to the one we just did, but it's not exactly the same. In this one, what we're going to have is we are going to, instead of putting cities on the stack, we're going to put tours on the stack. So up here in line 1, we come in and we say, okay, push a copy. This is not a function. We're calling push copy to push when we start, to push the partial tour 0 dash 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 on. So we start the stack with, I'm going to go down here, 0 dash dash dash. That's what gets put on the stack when we come into line 1. As long as there's no empty stack, we're going to say the current tour. And now up here, I'm going to have my current tour right here. So my current tour equals 0 dash dash dash. Okay. All this is just to give you an idea of what's happening here. I want you to be clear about what's happening in these algorithms. If the city count in the current tour is equal to 4, it's not. Skip that. From number equals number minus 1 to number greater than 1, if it's feasible to add that city, this is going to count down from 3, 2, and 1. If it's feasible to add that city, add it. So, and push it on the stack. So what it's going to do is it's going to add first the 3, and it's going to have 0, 3, and it's going to, by the way, we popped the stack, so the stack was empty. I'm going to do that real quick. Eraser, stack was empty. We put 0, 3, dash dash on here. That adds the city. We push that on the stack, and then we push that on the stack with the current tour, and that puts 0, 3 dash dash, and then we take the 3 off. So that's going to come off. We come back up here, and we're working the 2. So we push a 0, 2 dash dash on the stack, and then we remove that 2, so we're back at 0. Then we put a 0, 1 dash dash. Now our stack has 3 potential paths, and we then come back in here and we say, look, the current tour is now going to be 0, 1. That's what I'm working right now. Does it have N? No, it only has 2 cities. So now I'm going to come back in here again, and now I'm going to say, hey, could I make a 0, 1, 3? I certainly could. So that'll be the next thing that gets put on the stack. I popped the 0, 1. Sorry, I always forget to erase it. So this guy got erased. Oops, come on. Eraser. Here we go. I'm going to erase all this because we put 0, 1 up here, and then he's going to add 0, 1, 3 and 0, 1, 2. That's going to happen in this area. Then he's come back around. He's going to pop the next one, which is 0, 1, 2. And basically, this is going to keep going through these loops and it's going to build paths. Eventually, it's going to build a 0, 1, 2, 3 path. And when it does, that is going to trigger this up here. And it's going to say, hey, I found a path that's complete. It'll store that. Then it will pop that. It'll work back down the stack. Each time it works it back down the stack, it's going to pop a partial tour and add to it. Eventually, it will search every possible tour that there is. Okay. So again, you can take a little bit of time, work this algorithm, make sure you understand it. The three algorithms are, it's important that you understand. All right, so we have three algorithms. And now hopefully I'm done doing that relatively confusing, silly thing. So these three algorithms, the first one is recursive. We called ourselves. It didn't work very well because it had kind of a single thread, and there was one data structure. We couldn't break that up and share it among a bunch of threads, or among a bunch of processes. So so that one is not very good for us. Then we did a city stack, and the city stack is very efficient. It's not recursive. That's up here. I'm going to go to a laser pointer, I think, at this point. Where's there it is. Here's my laser pointer. This whole thick column on the left is talking about the city stack, the second algorithm. It is a serial algorithm. It's not recursive. Did not use a lot of memory because we weren't putting a lot of data onto our little stack. It's a little bit difficult to divide up the work using the stack because the stack doesn't have very much information. If you recall, the stack was just a collection of cities that kind of told us where we were, but didn't give us a lot of information. Now, we could parallelize it by starting some threads with each one having a stack state. For instance, I could do a breadth first search and create three unique subtrees and give each subtree to a process. But there's a limit to how much I can do that. And if I have 50 processors, it's just going to be very challenging for me to divide that up. It'd be possible, but it'd be hard. Meanwhile, over here on the right, we have a tour stack. Now, this is interesting. It uses more memory because every time we put something onto the stack, we're putting a full path on the stack. But the stack tells you where you are when you pop something off the stack. If you recall, you knew exactly what had been searched and what still needed to be searched. That means this guy could be easier to parallelize because we could put 10 threads out, and each thread could put stuff onto the stack, and anytime it pops something off the stack, it would pop off essentially a state or a data structure that tells exactly where it is. Now, this one is slower because we're constantly copying tours onto our stack. The one on the right, the city stack, is faster because it doesn't copy as much data. Some people might point out that, hey, you could push a pointer onto the stack and then you wouldn't have to move all this data around, but then we would have to have a bunch of shared memory and it wouldn't work at all in a distributed memory environment. And we want to have something that will work no matter whether we have a shared memory environment or a distributed memory environment. So we have three algorithms: a recursive algorithm, a city stack algorithm, and a tour stack algorithm. The recursive algorithm is very difficult to parallelize. The city stack algorithm, possible but not as easy. The tour stack algorithm, hey, this one has a lot of promise. We can parallelize it because it is easy to break up the stack and pull stuff. Anytime we pull something out of the stack, we know exactly what we need to do next. So we can have all the threads just pushing stuff onto and pulling stuff off of the stack, and they'll be able to be parallelized quite easy. So as we begin to think about parallelizing an algorithm, or we're going to do the third algorithm, we have to think about how the data is going to be organized. And so what are our main data structures? This is part of our process for parallelizing something. In our third algorithm, we have a tour. So that's going to be a structure that contains a list of cities and a cost so far. We also have a stack, and the stack is going to be a place to push these city tours and pull them off. We also have something called an adjacency matrix, and this is a matrix that we use to represent how far it is from one city to the next. And we'll show you that in just a little bit. All right, so here's what the data structures would look like in each of the two algorithms. In the city stack algorithm, the data structure would be very simple. We would have a stack, and we would add cities, and all we would have to do to add something would be to simply say, um, I'm going to make a stack pointer that points to the current location the stack is at. I'm going to assign my city number to that place in the stack pointer, represented as an array here. Then I'd make my size one bigger. That's it. We get a pointer to the top of the stack. We use the stack as an array, and then we just increase the pointer to the next array element. When we pop, we just reverse that. That puts the city onto the stack. Now, to push a tour, here you can see why it takes longer. To push a tour on, we have a stack thing, and the stack is an algorithm, is an array again of these um, tour structures. And so we first have to allocate some memory so we can store our tour. We then have to copy the tour into our new tour. We then have to copy the new tour onto the stack and increase the size of the stack. The function to do what we're doing is very simple, but it has to allocate memory and it has to copy a lot of data. That makes it slower than the city stack algorithm, unfortunately. All right. So Pacheco, if you look, he ran a size 15 map, 15 nodes. And this gives you an idea how complex this algorithm is. That generated 95 million tree nodes. 15 cities to visit generated 95 million possible paths. That's why it's so hard. Now, these are the times to run each of them on a serial implementation. And one of the things we noticed right away, hey, the recursive wasn't bad in terms of time, flat time. The and the city stack was even better, 29.2, and the one that copied tours was really quite bad. It's like almost 10% slower than the first iterative one. In fact, it is a little bit more than 10% slower. So you think, well, which of these should we try to use to parallelize? And you say you're kind of drawn to this first iterative one, and that turns out to be a bad choice because the first iterative version state is only a city number on the stack. It doesn't give us any context, and that makes it really hard to break the workup. But the second iterative version, even though it runs a little more slowly, it's actually easier to break up. And so this is the one we're going to choose. We're going to choose the second iterative version, the one that used a tour when it went on each stack. And so now we can kind of think about, well, how, now that we've chosen which algorithm we want to do, how do we parallelize that? Um, it's to me, these are very interesting. They're puzzles, right? What's the goal of the puzzle? We want to reorganize this algorithm so that it can be solved by a bunch of workers in parallel. What we're considering is, what do we have to think about? And if we were in class together, I would just ask you, hey, what kinds of things would you have to think about? And I hope you would say things like, well, what kind of underlying data structures do we have? Do we have shared memory or not? Which of the libraries are we going to use? Um, what data has to be shared among all of the processes, and what data can be kept private for each process as it runs? Those are the kinds of things you have to be thinking of. And as you think through that, you might begin to realize more and more algorithm 3 really is going to be easier to parallelize. So you ask yourself, here are some of those considerations I just talked about. How's the serial solution organized? From an algorithm standpoint, does it have loops? Oh, for loops. Oh, if there are for loops, oh, we don't have any of those. But if we did, that'd be nice. Does it have a single logic path like the recursive solution? That's bad. We don't. That's why we can't use that one. And then we begin to say, what are the data structures? Are there any shared ones? And in this case, the best known possible tour, all of the processes or all of the threads are going to have to know at any given time, what is the best tour we found so far? Because when they find a tour, they're going to compare it to that best tour. So there's a piece of critical data that has to be shared. So this is something that you'd have to think about when you are going through. Then, as I've already kind of mentioned, you would think about what are the underlying hardware factors, and do we have shared memory? Do we have um, distributed memory? If we have distributed memory, we're probably going to use MPI. If we have shared memory, we're probably going to use OpenMP. Fortunately, both of those can be used to implement the third algorithm. Another thing we might look at is, okay, we've got a tree, kind of a tree solution that we built with our self-managed recursion. And one thing we could do was, okay, we're going to build this tree out. Do we want to build it breadth first, or do we want to build deep on each arm of the tree, each branch of the tree? And what's going to be returned? What data is going to come back up the tree when we reach a leaf? And are we going to try to implement some min-max structures in our tree? These are the questions we have to ask ourselves. Um, we have a data structure. We're going to use the third algorithm called the best tour. That's mine, not Pacheco's. What does it hold? It holds the cities we visited in our best possible discovered tour so far. So if we had 4 cities, this would show the best path that we've discovered up until now. Ask yourself, who needs access to that? Well, every process or every thread needs access to it. Is it read only or do we have to write? Well, most of the time it's read only because the threads just come and ask, am I better than that? So they just have to read it. But when they actually find a better solution, then they're going to have to write to it. So writing to this shared piece of information is going to have to happen in a critical environment, or it's going to have to be handled carefully if we use OpenMPI. I mean MPI. Um, and so those are some questions we might have to ask. Now, another question we might do is how are we going to map the work to the nodes? And this is what I referred to earlier. Could we go depth first with threads at a higher level? Or do we want to do breadth first? If we go breadth first, then what we can do is we could have our 3 first step nodes each be a separate thread. If we had 20 possible steps, we could have 20 threads. Each thread could then run its own subtree. But here's an interesting problem. Some trees are going to be faster than other trees because they're going to quickly find a fast path, and they might have really high costs on all of their other branches. So, well, it's kind of challenging. You got to think, do we want to go breadth first or we want to go depth first? This is an interesting question. Um, if we go breadth first, the memory model is going to have its say about how that works. Otherwise, if we go depth first, not quite so much. So if we go breadth first, division of labor, then in a shared memory model with threads, every thread is going to have direct access to the best tour. And if they want to read it, they can do that, no problem. But what if they want to write to it? Then we have to avoid a race condition, and so we will have to use some kind of locking mechanism. And we only want to have one official copy, and you know the answer to that. If we're going to use threads in a shared memory model, we're going to use a critical feature that OpenMP gives us. In a distributed model, it's a little different. The process, when a process finds a new best tour, it actually doesn't have to share the tour with everybody. It just needs to share the value, and that's being used. And so MBI has a broadcast function, and we couldn't use it here because it blocks the sender. We could, though, have a process send a best tour value using a for loop, and every receiving process would not call MPI receive because it would block. Instead, they would use what's called MPI probe. So I'm thread 12 or process 12, and I find a new best tour. I send it to everybody else using a for loop, and I'm going to use a thing that says, hey, I don't want to wait. And then the guys that are possibly receiving it, when they come to that step in the algorithm where they say, hey, did I get a new best tour? They're not going to post a receive because they would hang. They're going to do a probe. The probe says, is there any data that's been sent to me? And then if there is, then they'll do a receive, but if not, they'll move on. So this is a way that the processes are going to communicate with each other, but they're not going to wait on the end. They're going to tentatively send something out. They're not going to wait on confirmation that it was received. And they're only going to check to see if they receive something new rather than always sitting there and waiting. So this is something you have to think about with MPI. Now, where do we put that in a distributed memory? There's a place where we check the tour to see if we just found a new best tour. Remember, it was up around line 5 or 6 in the algorithm. You go back to your text or download the other PowerPoint presentation from Blackboard and find that slide. It's called best tour. And in there, that's the only place where we ever actually have to look and see if we have a best tour, if ours is better. And so inside that function, that's where we could probe to see if we have a new, better algorithm, I mean, a better cost. And if we do have a better cost, That's where we'd receive it before we compare it. Once we receive it, it's ours. We don't have to worry. All right. So again, um, I mentioned that there's a buffered send. It's a minor variation on send, and it stores the data without blocking. Okay. Now, if we were using OpenMP, we could have a single thread. It could build out the first level, and then the partial tours could go on the stack. Now, since it's shared memory, every thread could just grab a part of the stack and work it. And if we use the second version, which is a third algorithm, we could store that entire tour on the stack. We wouldn't have to worry about it. We could just grab a tour off and work it. So then we could just assign each subtree of each node to a thread. And we still have to wonder how we're going to do that best tour. No problem. We're going to use the critical function. All right, I mentioned a little bit ago a data structure, and that data structure is called the adjacency matrix. In MPI, we can simply, no, wait, let me explain what this is. Notice the diagonal is 0. What this does is it says, how far is it from node 0 to node 0? How far is it from node 0 to 1? That one hasn't been filled in yet. How far is it if we go from 0 to 2? It's 3. So the adjacency matrix simply tells us how far it is from the city in the row to the city in the column. Notice from 2 to 1, it's 18. And you could go back and fill this in looking at the chart. I didn't do a very good job copying it out of my textbook, so I ended up with some incomplete information. You could fill that in. But basically, know this. The adjacency matrix is just simply a data structure that all of the threads, all the processes are going to have to go when they're asking, how far is it to go from node A to node B? Now, here's the question. Is it read only, or do you ever have to write? And the answer is read only. And since it's read only, you can just give everyone their own copy of it. It's static. It's not going to change. So this is a data structure that's actually pretty easy to implement. If we're on MPI, we send it to everyone. If we're on OpenMP, it's not critical. It's in shared memory. Everyone can just read it whenever they want to look at it. And that's how that would work. All right. Summary. Thanks for hanging in there. This has been a 42-minute recorded lecture with my dog that I'm babysitting, Shadow. And sometimes you get, oh, Shadow's jumping up my lap. The traveling salesperson problem gives us a different kind of problem to think about for parallelization. It's not a for loop that we can just easily break up. And we learn from looking at it that before we can parallelize a program, we really have to understand the data structures. Is there any critical data structures? We have to understand what things have to be shared, what things have to be kept current among all the processes or threads. And also we have to ask ourselves, are the algorithms we're looking at, are they single threaded to where we can't actually even parallelize them at all? Is it easy to break up? Remember algorithm 2, not hard to break up, but when you pull something off the stack, you have no idea because you just pull a number off the stack. So it's not possible for a thread to just go grab something off the stack and start working it. Meanwhile, on algorithm 3, we found that, hey, this one offers a lot of promise, right? So we looked at the algorithms themselves and found that one algorithm was going to be easier to parallelize and give us a better chance for efficiency. And then we ask ourselves, what tools do we have? Are we going to use OpenMP or MPI? Which one's going to work better? There's some judgment in there. When we looked at algorithm 3, it turned out sorry, this dog is driving me nuts. When we looked at algorithm 3, we found out that that one was a little easy to parallelize. All right, and then finally, what's the architecture we have? If we have a distributed memory or a shared memory, that's actually going to drive exactly what we have. All right, I'm told that the course evaluation is open, and I'm supposed to be getting access to see who has turned in the course evaluation. And so what I'm going to ask you to do tonight as you watch this, as you finish watching this, is go to your sections on MyOC and click on this course and do the course evaluation for me. I'd appreciate your feedback. And I will not know, again, you guys know how this works. I won't know what your feedback is until after the grades are submitted, so you don't have to worry about any kind of thing like that. If I see that you have submitted a course evaluation, I will give you 3 bonus points on your total grade. So that hopefully will incent some of you to go ahead and do that. I appreciate you for taking the course. And remember, have your homework in by 5 o'clock Friday. Next week we have an exam. Have a great day.